Hey everybody, today we're going to be going over how to do and analyze our mini lab activity about the density of metals. Now to get started, you're going to want to make a copy of this Google document for yourself for editing. Maybe title it with your last name at the end. And now that you've got your own copy, make sure to put your name in. We've got a summary here that tells what you're going to be doing, the overall objective, and the purpose is going to kind of be a restatement of that. For a good purpose, what is the overall goal? It's not the goal is to learn about this or that. The purpose really is what is the final calculation? What are you actually trying to determine in this activity? And so you can see in the summary, or if you scroll down and look at some of the last calculations, aside from percent error, you're calculating the density of a metal. In the summary, it says you're looking at the relationships between the volume, mass, and density of various pieces of the same metal. And so your overall purpose could be either both of those things restated, or just one, or just the other. So you could say the purpose of this activity is to investigate how volume, mass, and density are related for different pieces of the same material. Or you could say that the purpose is to find the density of this metal. Or if you didn't know what the metal was, it would be to confirm or identify what metal it is based on the density. Here, the measurements that are going to be taken, or the calculations, you would say that the volume of each piece of metal is going to be taken, and that the mass of each piece of metal. And then the ratio of mass to volume will be the density. That will be the measurements and the general overview of the calculations. Now, some type of prediction should be made, and that can either be a prediction about what will happen in the reaction or the experiment, or what might some sources of error be. And so in this, it's fairly easy to look up and find that what should happen is that as the volume is larger for a piece of metal that is the same piece as others, the mass should also be larger. And that's because density, which is a ratio of mass to volume, is the same for the same material. And so if it is larger, it must also be more massive. The density for all three pieces should be the same. Another prediction should be that when you graph mass as the dependent variable and volume as the independent variable, the y and x axes respectively, that you should have a straight line. There should be a direct relationship with the line growing from the left to the right. Some predictions about experimental design or errors, there are not really a whole lot on here. The balances are very precise, and usually it's if a piece of lab equipment isn't good at measuring, then that is considered to be a source of error. But everything that we're using today is pretty precise. The balances, the graduated cylinders, each will give at least 3 significant figures, which is generally considered pretty good for high school or even college labs. 3 significant figures in your measurements is good. The one thing I would say, if you're looking at your graduated cylinders, you'd notice that there are bubbles in the water. And so those bubbles might be adding to the volume, and when the bubbles float to the top, it might be affecting your volume aside from just putting the piece of metal in. Now, for this procedure, you're going to be getting 3 pieces of metal that are made of the same metal. Your options are steel, stainless steel, brass, copper, or aluminum. I'm going to do this trial with brass, and so I can get rid of the others. Your first step, because the three pieces are not labeled, is that you're going to draw sketches of them here. We're going to be measuring their volume by water displacement. That means that for each one, we're going to have a graduated cylinder with just water, and we would mark that volume here. And then we would gently slide in the piece of metal and see how much the water level goes up by. We would then dry that piece of metal off and take its mass and make observations about its color, other properties, if it's magnetic, and things like that. When you're filling up your graduated cylinder for water displacement, you'll want to make sure that the water level is at least as high as the piece of metal. We're using graduated cylinders where the piece of metal will still fit in. Remember to get at eye level to measure the volumes. And in this graduated cylinder, you can see that the markings, there's a marking here for 10 milliliters and here for 15. And each of the smallest marks then is half of a milliliter. So we can see like this would be 10, this would be 10.5, this would be 11, 11.5, and 12. Because the smallest markings are 0.5 milliliters, our known digits are the tens and the ones place, and our estimated digit is the tenths place. And so we could call this 12.0 milliliters. When you slide your piece of metal in for this water displacement, it's important not to splash, and so you're going to tilt the graduated cylinder as much as possible so that the metal slowly and gently slides in. You'll then again look at the water level at eye level. So here this is 20, this would be 19.5, and this line would be 19. And so our known digits, the 1 and the 9 for 19 milliliters, and our estimated digit is going to be somewhere between 0 and 5 in the tenths place. I'm going to go with 19.2 milliliters. The next step is to get the mass of this piece of metal. So I'm going to pour out the water, catch the piece of brass, dry it off, and put it on the quadruple beam balance. You can see that this quadruple beam balance is zeroed out. When every marking is at 0, it balances here, these two lines. If not, you'll want to adjust this end screw until it does balance. Now that I've gotten this to balance with these two lines, I'm going to read the measurement. 0 for the hundreds place, 6 for the tens place, a 1 for the ones place, so it's 61 point something grams. The tenths place is going to be 0.1. Each of these smallest lines is the hundredths place for grams, and so you can see it's 0.11, 0.12, 0.13, 0.14. And because it looks like it's right on the 0.14, and because each of these is 0.01 grams, we need to go to 1 decimal place further to 3 decimal places. So I'm going to report this as 61.140 grams. All right, so I ran into some trouble when I was using the 25 milliliter graduated cylinder with these pieces of metal. I went to go and put in this rectangular prism in after I'd carefully measured the water, and it got stuck. So make sure ahead of time that you're using a graduated cylinder that will fit your pieces of metal. So I already did this piece, didn't record it, but I'll show you how that works. You're going to use at least a 50 milliliter graduated cylinder. It'll still give you the same amount of precision because each marking here is worth 1 milliliter, which means that all of your measurements will go to the 10th of a milliliter. All your measurements should have 1 decimal place in this. Thanks to Hiba for letting me use her 50 milliliter graduated cylinder today. Next, I'm going to show you how to work with your data to perform some calculations and format them correctly, including full explanations. One thing to get out of the way, grammatically, the word data is plural. And so the word data really is referring to a set of numbers and observations, which also are plural. And so when you use the word data, grammatically, it should be able to be replaced with the word numbers. And so you wouldn't say, the data shows us such and such. You'd say, the data show us such and such. It's plural. So we'll move on to the calculations. In words, you're going to describe your calculations, and your calculations for this course are either going to be typically addition, subtraction, multiplication, or division. But in words, you describe them as a sum as addition, a difference as subtraction, a product as multiplication, or a ratio for division. So in words, the volume of the metal, it's going to be the final volume subtracting the initial volume of water, which means it's going to be the difference between the final volume and the initial volume. Next, to write a formula, you would have variables, but not numbers. You can use the insert equation function if you're going to do this electronically, or you could write this out on paper if you're going to take a photograph and submit it. Whenever you're referring to the volume of a specific thing, you would have V for volume, either capital or lowercase would be fine, and then you want to do a subscript for what specific thing you're talking about. So now we have the formula that the volume of the metal is equal to the final volume minus the initial volume. We'll next show one example using actual data. So the volume of the metal would be the final volume in the graduated cylinder, in this case 19.2, subtracting the initial volume in the graduated cylinder, in this case 12.0. Now in this case, the answer that a calculator would give us is the same as sig fig rules would dictate. This is subtraction, and so we're going by place value. This measurement goes to the tenths place, as does this one, and so our answer should go to the tenths place. It's 7.2 milliliters for the volume of the cylinder. Next, we would report the volumes of all 3 pieces of metal. We don't need to show our work anymore, but you would just show them with correct significant figures and units. So this is a fully explained, correctly formatted set of calculations for the volume of the metal. Next, we'll look at the density of the metal. Density is going to be the mass divided by the volume of something, which means since it's divided, it is a ratio. So we would say that it's the ratio of the mass to volume for an object. Next, we would write the formula. So D equals M divided by V. And we'll do one example, the same one that we did for the volume. It's going to be the cylinder. And our calculator gives us an answer of 8.491666666, repeating, of course. And so we're going to need to round that for correct sig figs. Since this is division, it follows the rule based on number of sig figs. The top number, the mass, has 5 significant figures. The bottom number, the volume, has only 2 significant figures. And so our final answer needs to be rounded only to 2 significant figures. And the units are grams per milliliter, since we had a number of grams divided by a number of milliliters. Next, we'll report out the densities of all the pieces of metal here. So you can see with all of these that they were fairly close, which was part of our prediction, part of our purpose, that we predicted that since density is the same for a substance, no matter how large or small, that no matter how large or small the pieces of brass were, that they would have the same density. And you can see they pretty much do when you round for sig figs, 8.5 grams per milliliter, 8.3, and 8.5. We're going to calculate the average density of the metal, and the average, you're going to add up all of the densities and divide by 3 in this case. But in words, to describe how to calculate the average density is that it's, because addition is the sum of the densities divided by the number of objects. Next is to write a formula. The symbol for sum is the Greek sigma, and the symbol for a number of objects is a lowercase n. And now to show our work, it would be that the average is 8.5 plus 8.3 plus 8.5 divided by 3. Now, in terms of sig fig rules, that number 3 is actually an exact number. We had exactly 3 densities, and so the number 3 does not affect our significant figures. What will affect our significant figures will be that on the top we have 8.5 plus 8.3 plus 8.5, which is 25.3. And that now has 3 significant figures when you take into account the addition rules. You're still going to the tens place, so it's 25.3 divided by 3, which gives an answer with correct rounding of 8.43. Percent error, if you look it up, is how far off were you compared to how much you should have gotten, and then expressed as a percent. And so it's the difference between the observed value, which is what you found in your experiment, the difference between this and the accepted value, which is what you would look up as the density of brass, is the difference between those two divided by what we should have gotten, which is the accepted value, and then times 100. So because the difference between the experimental and accepted value is going to be divided, I chose to say ratio at the beginning. It's a ratio of this difference to the accepted value expressed as a percent. The formula is going to look like this. And now I'm going to copy this formula into the next line and replace the numbers that would go in for what should be there. Now, in terms of significant figures, because the accepted value of brass is reported to only the tenths place, these two things are actually the same. So 8.43 minus 8.4 is 0.03, but it has to be rounded up to the tenths place. So really that is 0. And so 0 divided by 8.4 and then times 100 is 0% error. Next, I'll show you how to format these and graph these in Logger Pro. So the first step is going to be to input your data. And you really only have two columns here, X and Y. It's going to graph weird at first until we format that. But first, because we have 3 columns of data that we collected, we're going to need to add a new manual column. That's under Data and New Manual Column. We'll name these later. So X, because it's the first column on the data sheet, will be the initial volume in the graduated cylinder. You double click at the heading to get the options. We have a long name, the initial volume. The short name, I'm going to put V sub I for initial volume. It doesn't give me an option for a subscript I, so I'm going to just put V and then lowercase I in parentheses. Then the units are milliliters, lowercase m, capital L. Now these are all formatted for data input. You can see any of these measurements that ended with a 0, it kind of cut them off, and so we've got to reformat those by looking at the options. And we want these to be 1 decimal place for the volumes, and for the masses, 3 decimal places. Next, we're going to do our calculations in the columns, and so we're going to add in calculated columns for the volume of the metal and for the density of the metal. Now, when you do a calculated column, the expression is the calculation you want it to do. And you're going to use variables to refer to different columns. So we're going to say that we want the variable to be the final volume minus the initial volume. We'll hit done. You can see that it calculates the volumes here. We want to reformat that because according to sig fig rules, it should only be going to 1 decimal place. Next, we'll do a calculated column for the densities of the metals. And the expression is going to be that it's the mass divided by the volume of the metal. So we're going to pick the variable mass divided by the variable volume of metal and hit done. Again, we need to reformat this because the volume of metal, those all had 2 significant figures. This division problem should only have 2 significant figures. That's our data table. It shows us the same results for calculations as we had before. The graph, though, is not graphing what we want it to. We want our graph to be the volume on the x-axis and the mass on the y-axis. So the way we do that is by right-clicking and selecting graph options. And first, we'll go to axes options. On the y-axis, we want it to be mass. And on the x-axis here, we want it to be the volume of the metal. We'll hit done and see how that looks. We can see that it's only taking up this small section of the graph. So we want to auto scale the graph, but it cuts off the beginning. For this type of graph, we're actually going to want to auto scale from 0. I right-clicked to get that, that menu up. We're going to want to finish formatting the graph. Under graph options, we want to include a title. A title should say something about what the experiment is or what variables are being measured. And in this case, because it's going to be a straight line, we want to have a line of best fit. So if you hover over, you'll see that a linear fit. We click this and we get this line that goes through, and it goes pretty much through the point 0, 0, which is a good sign for this, because if a piece of metal had 0 volume, you would expect it also to have 0 mass. And notice that this slope, 8.3, is very close to the densities that were reported. But density is not only a ratio of the mass to volume of an object, but when you graph mass to volume, because the slope of a line is the y values divided by the x values, you get that this slope is pretty much the density. So we're going to paste this in. If you click on the graph, notice how these boxes show up. All you have to do is hit Control-C. Then you open up your graph. And I'm going to delete this because all of those things are on there. We'll check the graphing checklist in a moment. And Control-V is to paste in the graph. We're going to check out the graphing checklist here just to make sure everything is there. Descriptive relevant title is checked. The axes are labeled. We have units on all the axes because of how I formatted the columns. The points are plotted correctly. Logger Pro does that, but if you were doing this by hand, that would be an important thing to pay attention to. There's a best fit line, if appropriate. It was here. The points were not connected because it was not this type of experiment. A data table with column labels. So now what we'll need to do is go back to Logger Pro, and now we select the data table. And notice how when I click on it, these boxes show up. The same thing should happen if I hit Control-C and then go back to the lab. I'll put underneath the graph So as you could see, it was kind of formatting things weird. So what's going to be a better solution in this case is to take a screenshot. And on a Windows computer, that means you would hit the blue function key and then F11, so it says print screen. And then here you would hit Control-V and paste in. Now here you would just go and crop the image. So I'm going to take everything out except for that data table that I was trying to get before. And then once I have that cropped, I can enlarge it so it looks better. So there we go. That was the Logger Pro stuff. Everything looks nice. The one thing that was on the checklist that I kind of glossed over is a description. So we're going to describe what is happening in this graph. That a linear relationship that starts low and goes up is called a direct relationship. So this is showing a direct relationship between the mass and volume of pieces of brass. Now last, we're going to look at the analysis and conclusion. So the claim that addresses the original purpose. The original purpose you could have stated if it was to look at the relationship between mass and volume and density of different pieces of the same material. Your claim could be that the mass and volume are directly related or have a direct linear relationship. So as one gets larger, so does the other. The density was constant for all the pieces of the same material. The evidence, you could say that the data, when graphed, when the mass and volume data were graphed, that there was a straight line with a high R value or an R value close to 1, which means very close to linear. You could say that the densities that all were calculated were very similar to each other. You could say that as the volumes got bigger, so did the mass. The scientific principle here is that density is what's called an intrinsic factor, meaning that it does not matter the size of the sample. As long as it's the same material, it will be the same. So things like color. A piece of brass will always be the same color, and a piece of brass will always have the same density, because density is a ratio of mass to volume. No matter how big a piece of brass you have, it will always have the same density as a smaller piece of brass. The errors in the measurements, I ended up with a 0% error, but things like if you did not fully dry your piece of metal before putting it on the balance, that means your mass would be too high. And because the mass is in the numerator, that means your density would be too high. If you didn't dry off your piece of metal, your density would be too high because your mass of metal would be too high. You think that you're measuring just the mass of the metal, but you're also measuring the mass of a little bit of water. Some other things, if you drop in your piece of metal and your piece of metal has air bubbles around it, that would make the volume appear to be higher than it really is, because you're measuring the volume of the metal plus any air bubbles. And the volume, because it's on the denominator side for density, if the volume was higher than it should have been, your density would have been lower than it should have been. So if you did end up with a % error, you would see if you were too high or too low compared to the accepted density of your material. If it was too high, then it's probably that your piece of metal was wet when you measured its mass. If it's too low, your density is too low, possibly because your volume was too high, because maybe you were measuring the volume of air bubbles that were attached to your piece of metal. And that really gets at these last prompts completely by analyzing your sources of error. So this has been really detailed. We're pretty much giving you everything you should need for this lab, as long as you take the time to really watch this. We wanted to make sure that you were starting off the year with some good models about how to show these skills, and hopefully you remember them and can carry them through for other activities that we do. Good luck putting this together.